to the second speaker, who is Hagen Holthusen, who is a postdoc at FAU from the Institute of Applied Mechanics. The stage is yours.
Okay, thank you for this warm introduction. My name is Hagen Holthusen, and I just want to give you a talk about AI and mechanics. It's not such an in-depth talk, it's more like an overview of what is going on in the mechanics community, and I should say in the continuum mechanics community. So not fluids, it's more on solids. And of course, this is joint work together with some of my colleagues from Aachen, from Stanford, and also from Hamburg. So this talk is structured as follows. First, we start by AI and material modeling, and I guess most of you are mathematicians. So material modeling means you have a material and it's subjected to some kind of load, and it exhibits some stress behavior. And this could be different if you think about rubber in contrast to steel. So this is the very first part of the talk. The second is about AI and model order reduction, where we look at entire systems and we want to speed up the computation time. And lastly, it's more like an outlook. So what do we think where I will go in mechanics? And we call this AI and mechanical thinking. So let's start with the very first thing. As engineers, we always start with three equations, the so-called equilibrium. If you think about forces, so Newton mechanics, then forces should be in equilibrium. Second, we have the kinematics, which relates our solution variable. In our case, it's the displacement, with some gradient of the solution, and lastly the material law. And this is more or less heuristic. We know some mathematical properties it should have, but it's not that strict like the first two equations. So the equilibrium and the kinematics, they are really proven that they exist. The material law you must find somehow. And one of the famous approaches in AI is so-called physics-informed neural networks. So you have a normal neural network where you have a loss, which is, for example, the mean squared error between your prediction and the thing you measured. So, for example, the solution field, the displacement. And what they do in physics-informed neural networks is they add a physical loss in addition, and this is nothing but the PDE. So they include the PDE, and so the network is informed with the underlying physics. The problem is a little bit, okay, you must know the material law in that case. So to somehow connect the PDE or to put this PDE into the loss, you have to know the physical law or the material law, and this is not known a priori. So what we are focusing more on is, okay, how can we find this material law? And what we do is we look at the second law of thermodynamics, which states nothing but, okay, if you put ice into water, then the ice will melt and not the entire water will get ice. And if you plug or if you multiply everything out, you get a Helmholtz free energy with these properties. So it must be always greater to zero, it must be zero for no deformation, and this derivative must also be zero. And then you can connect the stress to this Helmholtz free energy. And the scalar function is much more easy to handle, at least for us, than a stress tensor. And what we then do is, you can call this constitutive artificial neural networks, physics augmented neural networks, or thermodynamics artificial neural networks. There are a lot of names in the literature, but they all do the very same. They plug in the deformation gradient. So this comes from the kinematics, where we have the gradient of our solution field, pass this through some network, and we manipulate the architecture. And we manipulate it in such a way that it fulfills certain requirements. So these first three, and due to objectivity, so for example, you and I must measure the very same energy regardless where we're standing or how do we rotate, and it must be so-called polyconvex. It must be convex with respect to all the invariants of the deformation. And if you do so, then you guarantee at least that you a priori satisfy physics. And this is what we do next. So This is a work from Kevin Linker from 2021, where they investigated rubber materials, and they constructed such a neural network. They made it arbitrarily large, and yeah, we had some data of the rubber, so we either stretched the rubber or we sheared it, and we plugged this in and trained the neural network on that. In the first case here, it's a single load training. This means, okay, the neural network sees either the stretching, the shearing, or some biaxial tension, so where you put or you stretch the material in both directions. What you see is if you feed the neural network with more and more data, so use something we call the multi-load training, then you get a somehow unique solution. So less terms in the neural network are active, and this is what we consider to be a unique solution, at least from an engineering point of view. And you could now ask, okay, it seems to work, so everything is done in physics, or at least from an engineering perspective, and luckily it's not. So most materials exhibit some so-called inelastic behavior. And the first problem is, the first known phenomenon is viscoelasticity. So it's more or less the resistance against flow. And you notice if you stand in front of a bus station and you look on the ground, see that there is some kind of, you see where the bus was driving. And from a micro's perspective, this is associated with the entanglement of polymer fibers or general fibers. So these over time entangle, and this is what you macroscopically observe with viscoelasticity. This is just one example for that. Then second, very famous, is elastoplasticity, which you could also refer to as irreversible deformations. And you see this here, this was a steel rod which was just pulled, and it breaks here at some certain point, but what you see is a necking in this red circle, and this necking is still present there after the failure. So there's no load transferred through the specimen anymore, but we have irreversible deformation. This is what we call elastoplasticity. And lastly, this is related to biological systems. So all of your cells behave like growth and remodeling behavior. This means the preferred state is not an unstretched one, rather than arteries and the heart and everything of that. It tries to achieve a so-called homeostatic stress state. So it contracts itself or it releases itself to achieve this preferred stress state. And all of this is inelasticity, so we want to model this also using neural networks. And what we then do is one of the famous or the most powerful approach, I would say, is the multiplicative decomposition, where we assume that the gradient of our solution field can be multiplicatively decomposed into elastic deformations, so they rise your stresses, and inelastic ones. And those inelastic stretches, or the part which are inelastic, they account for your dissipative nature of your material. Then you can define some stretch and inelastic stretch tensors, and in mechanics, we illustrate this with a mechanical potato. So this is your reference configuration, your initial state, your current state, and we fictitious or arbitrarily introduce an intermediate configuration, so due to this multiplicative decomposition. What we then do is, again, we evaluate the second law of thermodynamics. This must be greater or equal to 0 for all states possible. And there is one way to achieve this. This is not a physical law. This is just one very, I would say, powerful approach to do so. You, in analogy to the Helmholtz free energy, introduce a second potential, the so-called dissipation potential, and assume that this accounts then for your dissipative nature. You set then the rate of inelasticity equal to the derivative of this potential, so this reminds you very much on what you've seen for just purely elastic materials. And this brings us to the idea, okay, we do something similar. We plug in this so-called thermodynamic driving force, so some kind of stress, into the neural network, and we manipulate its architecture such that it is 0 for the 0 state, it's convex with respect to its input variable, and it's greater or equal to all non-zero states. And if you do so, you satisfy physics a priori. And this is at least what we want to do. So let's have a short look on how the network architecture may look like. So yeah, the very or the recurrent architecture is, so we have a time-dependent problem. You plug in your deformation and your time increment at some point in the time space. You calculate the elastic stretches, hand them in to the neural network for the Helmholtz free energy. From this, you get the input for your dissipation potential. Plug this again in. We have to solve an ODE, since we have an ordinary differential equation to solve for our inelastic stretches. And the solution of this is then very lastly plugged in again in the very same network to give us our stress. And we have to do this over time, so this is recurrent. And what we pass from one step to the other is nothing but the inelastic stretch. So this evolves or is passed through time. And how is this network architecture for the dissipation potential designed? We do not plug in directly the stress rather than the invariance. So this has again something to do with you and I should observe the very same physical behavior. So we have here our invariance. This accounts for the pressure. This accounts for shearing. And this somehow for the orientation of the maximum stress. So you can really somehow attribute physical means to those invariants. They are not chosen arbitrarily. And if you then say, okay, in the very first layer, we have just convex functions, and thereafter convex but non-decreasing ones, what you get is, and you get in the very last layer some non-negativity constraint, you satisfy a priori the second law of thermodynamics. And you can scale the width and the depth as you do it in normal neural networks. And yeah, you can scale this up and hopefully discover all the materials. So let's have a look on viscoelasticity, elastoplasticity, and growth example. And we start with some artificial data. What you see here is in the solid lines, this is the prediction of the neural networks. The dots are corresponding to the experiments. And from an engineering perspective, we also always like to illustrate this somehow. And this is what we call a Maxwell element or a generalized Maxwell element. So this here is called the dashboard, and this accounts for your dissipative nature, while this is a spring, and the spring you may consider to be responsible for the stress. And a viscoelastic solid always consists of a dashboard and a spring, and in parallel just a spring. So what should come out, at least what we expect to come out, is that one of those dashboards is discovered to be 0. But the problem is a little bit at the beginning, I'm not sure whether you can see this so good, is here we see, okay, the neural network discovers there is no dissipative nature at all in the data, hidden. And we attribute this somehow to the regularization we used is too strong, or the information entropy in the data is not huge enough. And what we did then next is, okay, instead of plugging in the full data, we used a staggered approach. So yeah, we decreased the batch size more or less. And what you then see is definitely, oh, now we are able to observe also this relaxation behavior. So this was a time where we keep the strain constant, but the stresses decrease. And this is what we call relaxation. And in fact, the weights we discovered, they indicate that one of those dashboards is 0. So yes, we have discovered what we already knew was hidden in the data. And we already published that, oh no, it's under revision, and one of the reviewers asked, okay, why do you use regularization at all? What is when you just give them the data and try to find out something? And we did so, and unfortunately, the result is the results are better. But what happens is that the network discovers, okay, both dashboard elements are active. So this is more what you assume to be a fluid. And then we say, okay, then if it's a fluid, you compress it and you wait for infinite amount of time, you will see that the stress will go to 0. And this was not the case here. And we ask ourselves, okay, how could this be? The fact is the potential which came out was way more complex than we expected. It was not what we call a standard potential. It was shifted by the maximum activation function, and therefore we had something like a threshold. So the dashboard element here behaves like, okay, if you are below some certain amount of stress, this dashboard closes. So there is no viscoelastic behavior. And this is possible from a physical point of view, but not very interpretable. So the question arises a little bit in mechanics, do we still learn something? So you get this out, but you do not know which kind of inelastic phenomenon is hidden in the data. So what we're facing is somehow the trade-off between interpretability of our model and expressivity. So the more general or the more flexible your network, you may less can interpret the result. Next thing was, this is really something from reality, not artificial data, we investigated tofu. What we wanted to find out is, okay, we have different types of kinds of tofu, and we are interested in, okay, is the mechanical behavior of those different? So we investigated extra firm, and silicon tofu, and we cutted it, and then investigated them on our own. And what we see is here, the neural network, I'm still not sure whether the light's a little bit too light. Okay, nevertheless, what you see is for the extra firm tofu, what we did was a compression test at 3 stages. So we compressed it, released it, compressed it, released it, and compressed it again. This is what we used for training. And for prediction, we compressed it, waited a little bit, and compressed it even more. And for the extra firm tofu, we see, okay, almost all of those invariants are active. This means the extra firm tofu reacts on hydrostatic pressure, it reacts on shearing, and it depends on how you apply the load. The firm tofu network looked a little bit different, and especially the silicon tofu, you see most pronounced is this third invariant. And why is this important? If you have 3 types of tofu, and the tofu just consists of soybeans and water, and you want to have a certain or specific material behavior, you can reverse engineer with a neural network, okay, what should be my amount of water to have this particular behavior? So, for example, you want to have it more resistance against shearing, or the hydrostatic pressure dependency should not be that high. This was what we wanted to figure out, and yeah, this is the point where we're standing. But it's interesting to see that the neural network really helps us to understand the mechanics or the underlying mechanics of a material. Lastly, we did this also for elasticity, and what we see is, okay, we just gave it the first load cycle, so these green dots are the training data, and the prediction is quite bad. And if you increase this, so you have a loading and the unloading cycle, your prediction gets better and better. This is known for experimental mechanical guys for decades, so you need to include cyclic behavior if you want to discover elastoplasticity, but it's nice to see that it's more or less the very same in neural networks. And we did this also for growth. This animation is a little bit too fast. And in growth, yeah, we conducted these experiments, or they were conducted in Hamburg. And what they did is they have a tissue-engineered specimen. You see this here in the dashed lines. This was the initial configuration. They just clamped it and did nothing with it. And I think you would say from your intuition, if you do nothing with a specimen, nothing will happen. And this is exactly what is not the case for growth and remodeling. So you just wait for a period of time, and it contracts itself to reach this homeostatic stress state, which you see here on the right. And we did the very same with our neural network approach and found, okay, there is some solution. We have some model discovered which is at least able to discover this phenomenon of homeostasis. The problem was a little bit, we then after that plugged this into a structural simulation, and at some state in time, we see an unstable behavior. So more or less everything crushed to 0. And the problem was, certainly, this is one-dimensional data. We have a 3-dimensional problem. Obviously, the solution state is non-unique. So we need more and more data, and hopefully then also on the structural case, this will get better. For the second part of the talk, I want to talk a little bit with you about AI and model order reduction, as structure simulation takes a lot of time, and we should decrease this computational effort. What you do in what is called intrusive model order reduction, you have a full order system, so you have your stiffness matrix, you have your solution field phi, and you have some right-hand side vector. And this is solved normally iteratively to solve for your PDE. And this could take quite an amount of time. So if you have, I don't know, 3 million nodes with 3 degrees of freedom, it's 9 million degrees of freedom in total. So you want to somehow decrease that. And what you do is you apply a subspace projection. So for example, using a single value decomposition, you construct here your projection basis xi, and then solve for this reduced system somehow, and then project everything back. The problem is you need access to the solver, and more importantly, if your system is nonlinear in, for example, the stiffness, and also if you want to interpolate some states in between which were not included in constructing the snapshot matrix, you need to interpolate. And this is, at least for us, not a trivial task, but an alternative is non-intrusive or AI-based model order reduction. And what we're using is an autoencoder. So you have your solution field and you compress, or you somehow encode the data into the latent space. Then you use a decoder and get back to your original field, and somehow try, during the training, decrease the error between the reconstructed field and the original field. And if you then want to predict some states in between, what is done is, first of all, this is unsupervised training, so you just plug in everything you need in your parametric space. So for example, if you change the geometry, if you change the material parameters of your material, everything is plugged in an unsupervised manner. And the state thereafter, if you have trained your autoencoder, is supervised latent space prediction. So we use a second regression neural network. This could be a standard feed-forward network. And then you really connect the parameters, like the geometry you have changed or the parameters you have changed, to the solution field and try to approximate the latent space. And if everything is trained, you just connect this and get to an end-to-end model where for some states in between, you can predict the states or the solution field. And let's have a look on how this works. So first of all, the anisotropy. This means you have a plate, you load it with a constant traction, so you somehow pull it to the right. But what you include is some fibers. And these fibers, will somehow deform it arbitrarily. And what we then did is we parameterized this angle here. And for training, we used some finite states for the fiber angle and plugged this into the autoencoder, and then thereafter trained the regression network and look at the prediction. And what you see here, the black outer lines, this is the full order model reference solution, and in between, this is just the prediction by the autoencoder. So what we see is that at least the shape seems to fit very well from what we see from the full order model, but the computation times are, I don't know, this normal FEM simulation takes minutes. You can look how the solver solves it with the Newton iteration, and this entire stuff less than 10 milliseconds. So from an engineering perspective, again, this is quite useful. And also if you try to, or think about combining this with physics-informed neural networks from the very first part of the talk. Something more recent is where we want to build a digital twin for roads. So the idea is you plug in some sensors in your streets, and then you can maintain the streets in real time. So we have our sensor data, and this then measures, for example, how a car is driving across the street. And this is then plugged into a FEM simulation. And what you see on the top is the displacement. On the bottom, this is the damage or the degradation occurring in the street. And if you do this with FEM calculation, obviously, this takes longer than a car is driving across the road. So therefore, we want to use this non-intrusive or AI-based model order reduction to get closer to real-time simulations. And we did this, so for the displacement fields, this is the displacement in the thickness direction of the street, and here you see again the damage field. So this is a multi-field problem. Damage is considered as a multi-field problem, so like temperature, you also have a field for the damage. And at least our reference, as well as our non-intrusive AI-based solution, for both the displacement as well as for the damage, I would say they are close enough to each other. And this whole process, so this evaluation, takes us roughly 150 milliseconds. Of course, this does not include the training, but if you have once trained your autoencoder, you can really get to real-time simulations of your street and may maintain it. And the very last thing for AI and model order reduction, we have here some microstructure. This is a composite material. You have some matrix, could be rubber, whatever, and some inclusions, for example, steel. And we trained it. Again, what we parameterized was one time the loading, so how do we load this, and in addition, the stiffness ratio between matrix and inclusion. What we see is that the gradient in the y direction for the displacement between the reference and the non-intrusive AI, they fit quite well for a standard neural network. You can improve this if you're using convolutional or graph neural networks, but already with this standard feed-forward network, we were quite satisfied. And what we then asked ourselves was, okay, can we reconstruct the reaction force under Dirichlet boundary conditions? Because this is also quite important for maintaining, or also if you train a physically informed neural networks, you need the reaction forces. And the idea was, okay, we have here our latent space, and some people in the literature claim we encode their physics. And if we do so, then this would mean, okay, if you have the full solution field, except for the boundary conditions, there is some, or there should be some way to reconstruct the reaction force. But what we see is we did not. So we increased the standard feed-forward network more and more. So we increased the width, we increased the depth. Maybe we did something wrong, but we were really not able to reconstruct the reaction force just from the latent space we have previously discovered. So the magnitudes are 10 times higher, and also the contour plots, they are way off. What we did then next was, okay, we enhanced the latent space, so we provided it with some information about the reaction force, and then we see, okay, we are able to reconstruct it. But the question arises, do we really encode physics? So related also a little bit to the talk yesterday, the idea was, okay, can we learn something from the compressed data? Because then this would give us an idea how we can design a material if we know the underlying physics for some specific system. Which brings me to the very last part. This is really more or less an outlook. This is not ongoing work. But what has AI done for us in mechanics? So when I studied, I had to learn some of those potentials. So to say, okay, this is a potential you may use for, I think this was some polymer stuff. And AI has relieved me from, first of all, finding the parameters, and in addition, finding this equation. So we now discovered the best model with the best parameters. And in addition, some people claim, okay, AI decreases our knowledge. I wouldn't agree on that, because it opened at least my eyes for thinking about, okay, what do all inelastic phenomena have in common? So how can I model all inelastic phenomena at once? And again, also, how can I interpret my results? How can I generalize this? And what is the underlying mathematical structure? So what could be the next step? And I thought a little bit, okay, how do we teach mechanics? So we have a teacher, we have a student, and if you just throw in the equations, what you get back from the student is, at least to my experience, more or less nothing except for question marks. But you want to have new ideas. We want to have PhD students, we want to have researchers which drive us, for example, AI and mechanics. And what we did, or at least what we do normally, is we provide pictures. So when I'm thinking about mechanics, or when I'm thinking about a system and its load, and I have an idea how it deforms, it never ever has something to do with equations. It more or less has something to do with pictures, or you can roughly say with pattern recognition. If you provide the student with this, what you get is hopefully new ideas how to construct something, how to improve hybrid hardware, instant restenosis across the fields. And I would say this is the better idea, and maybe you can transfer this on AI as well. So what we have achieved so far is we have somehow strongly enforcing physics network. the scan stuff from the very beginning, where you really a priori satisfy physics. We have this model order reduction to give you a fast prediction on how a system is behaving. What is missing is a little bit on, okay, we are quite good in the parametric regime or where we have parameterized, but if you go outside of this, this is horrible. And this is, up to now, contrast to humans. If I change the load and ask a student, okay, how will it behave, the student has an idea. And most of the time is better compared to the prediction of a neural network. So we must increase this. Maybe we connect this fast prediction somehow with the physics or increase the data set, of course. You can always increase the data set. The problem is a little bit, at least if you want to increase the data set with experiments in mechanics are quite time consuming. So we somehow must circumvent this problem. But the thing is, if you have a good predictor, they may say or may tell you, okay, some localization, so some inelastic phenomenon happens in this area, and then you can say, okay, my dissipation potential is trained on the stress values I measured really in this area, and my elastic Helmholtz free energy in all the other cases. Because what we do now is we train all the networks on the entire specimen. This might be faster. What we need in addition is somehow the coupling between fields. And this could be temperature, so temperature and mechanics, but I would say this is not that interesting. You know the underlying physics, you just have to somehow change the architecture. More interestingly is if you go to biological regime, so for example, we have here an artery and there's a stent in between, and what you see is the restenosis. So your artery grows again around the stent and closes the artery. What you need is a drug-eluting stent to prevent this. However, to have the right amount of drug eluting, you must know how all those PDEs, so the reaction diffusion equations or the underlying PDEs, are coupled to each other. And there's no physical law compared to thermomechanics describing this for you. And a colleague of mine did this in his PhD, and I think he coupled 5 or 6 PDEs and had just rough an idea how they are coupled. So really we need an AI tool finding for us the relation and also telling us, okay, this and this is the reason. So not just data-driven ones. And very lastly is design. So if you think about, okay, the tofu stuff, you want to have this and this food experience, or you want that your material is very resistant against heat or whatever, you need a design tool. So more or less inverse AI. And in between, so these are all singular tools, but they must be connected. And this is, I think, an ongoing work in the AI community as well. So you have agent-based AI. You have some agent in between, or also agentic AI, so which does this all autonomously and connects these expert networks. So you have one expert for predicting, one for physics, and so on. And the agent in between connects the answers of all of them. And of course, this is not my idea, so you see this in a multiple field, but also again a little bit what was said yesterday. Let the others do the work for you. And for example, in the gaming industry, we see real-time learning, strategic adaptation, and multimodal AI. So where you have different inputs, speech, voice, whatever. And hopefully we can transfer this to mechanics, so to apply it, at least at the very end. And with this, I want to thank you for your attention and looking for your questions.
Thank you, Hagen. I would start with a question. Usually, intrusive model order reduction is used because it's used to preserve properties of solutions. For example, I think of contact mechanics problems in which you have to preserve, for example, the non-interpenetration constraint. But there are also a lot of other examples, like you have to enforce the positivity of the solution, and we know how to do that, how to preserve these properties in standard non-intrusive model order reduction, I'm asking myself how to guarantee these properties in the non-intrusive techniques.
So the short answer is, at least to my knowledge, there is no way to guarantee this. But I think also in the intrusive model order reduction, you can somehow construct this for cases where you have a linear system. I'm not sure whether this, for example, is also possible if you go to the non-linear regime, and especially if you involve inelastic phenomena.
Mm-hmm.
I'm not sure whether you can still guarantee those properties.
Yeah, there are some structure preserving techniques which are able to do that. And
Okay.
I would also be happy to discuss later about hyperreduction because I work in it. So there are these techniques that are enable you to have a very small computational cost, also with non-linear terms or non-affine terms in parameters. For example, now I'm working in discrete empirical interpolation methods, so I can tell you a bit about this.
Yeah, for sure. Yeah, one of my colleagues is, he started on that, but now he's doing this ECSV, so energy conserving sampling technique.
Yeah, I know that, yeah.
But I still think you have a problem when your system behaves nonlinear, for example, on some material properties.
Yeah, this is exactly the objective of the techniques. And but of course, it comes at a price because you have a larger training cost. So this also brings me to the following question. Have you compared the training cost for the 2 meters?
So we really started on that, and our goal was just really to decrease the online computation time, and at least to what we experienced now is that we are faster using this non-intrusive approach. Nevertheless, there is more or less a miracle in between, because you do not know what the neural network is doing for you.
Okay, so you don't have, for example, the speed up with respect to the full order model?
No.
Okay, I see. Okay, thanks. Are there any questions? Okay, so thank you very much again.